Okay, here we go. So, how... Sorry, I don't know why it's flickering there. I'll just do that. There we go. That should be... So, one of the things we got here, Module 6, IQ1, technology. Okay, so you guys are all today, we're doing the Kahoot just by mobile stuff. Just makes it a hell of a lot easier. And one of the things there, I know a lot of you teachers, a lot of people in education say, oh my God, mobile phones and all that's the end of the thing there. I've been doing good stuff for ages. Interesting thing about that photo, I can't remember exactly, well, I don't know where that comes from. 100 years ago, there was an article in the Sydney Morning Herald said that the rise of the combustion engine is going to be great for pollution. Because how did you get from Parramatta to Sydney 100 years ago? Right? You could have gone by train, yes, but if you couldn't afford the train, you actually rode your horse. A lot of cities 100 years ago, they said the petrol car was going to be awesome because it would get rid of all the horse crap on the street. How ironic in some ways. It's actually also slower to get from Sydney to Parramatta now than it was riding a horse, I think, because of traffic. Now, for some reason, okay, this is going to get a little bit funny here. For some reason, I don't know why, the fonts aren't working well. I thought I had actually checked that there. Okay, sometimes just technology just doesn't want to work for you. So we've already done the Kahoot. Okay, so how can technology be used in the following cases? Now, in the syllabus, you're given 4 cases here. One of them is temperature on reaction rate. Now, that's pretty much a self-evident thing there. What's the relationship between temperature and reaction rate? If you do something to temperature, what does it do to the reaction? Yeah, a few people sort of said there. As you increase temperature, reaction rate. We also got temperature and volume of gas, speed and distance travelled, and pressure and volume. Okay, so what we need to do, let's have a look here. We have one of the things there, design a practical to assess, blah, blah, blah. What you should get here is, that's your little thing there we gave before, boiling water, put the big glass thingy on the metal thingy and then put the hot thingy underneath. You do it a little bit better than that. Now, what you should essentially get there is that if you increase temperature, you increase reaction rate. Now, I've just sort of got that from a couple of things there. Probably in most cases there, you might think there's a linear relationship and that there, but that's fine. Temperature and volume of gas. How is temperature going to affect volume? Temperature and volume, how's that going to be affected one by the other? What happens when you increase temperature? What was that? Volume increases. Okay, so we should get here this sort of thing here, which in chemistry is called Charles's law. Now, why, not necessarily in the syllabus, but it's a good thing to know, why do you think the volume increases when you increase the temperature? What do we have? Expands. Why does it expand? Particles get more excited. Awesome. They get more excited, and that's your particle theory of matter. They get more excited, they push, and then you get that going out there. Now, speed on distance travelled. I've got to admit, this was kind of a weird... my background is physics, but when they just said, the relationship between speed and distance travelled, it was like, well, if you go faster, you travel further. That's essentially it. So this was a good graphic here because it sort of did a lot of things there. So you got distance and time, which is your standard way of doing this. And so, yeah, if you're fast at a steady speed, you go further distance in a shorter amount of time. This is probably what most of you do. You're getting faster there. Or if you're really unfit like me, you go really far, then you got to rest and go back. Okay? And you millennials and Zers on your phones are probably like that as well. Pressure on volume of gas. What happens if you increase pressure? It's going to go down. So this is a thing called Boyle's law. Now here I'm going to test a few of you a little bit here. Who here's doing at least 2 3-unit maths? Yeah? What type of curve is that? Hyperbola. What's happening here? Asymptotic curve. Awesome, well done. Okay, so essentially you're going to get down here. Boyle's law essentially is that it's going to be an asymptotic curve. Why can the volume never be zero? Because that would mean that pressure would be infinite. Yeah, you have, but basically when you're increasing the pressure, so you might have done this, often you actually do this in year 7 and never think about it again. You might have at school, you've got the experimental apparatus, essentially a syringe on a bit of wood, and you push down, and you keep on pushing, and the more force you go down there, but you can never compress the air beyond a certain point. Now, if you kept on putting pressure, if you're strong enough to do that, you get down to a point there. In fact, you get to a point where the air would turn into a liquid, and then eventually turn into a solid. You can't actually get to zero volume because there's still particles in there. Okay, so that's what happens with that there. Now, one of the things there, you've got to assess the limitations of the technology used. So I'm going to just go back up here a second. The easiest one here for me as a physicist background, speed on distance travelled. What sort of technology can you use to do that? What sort of technology can you use to measure speed, distance travelled? You can think of really easy ones. Stopwatch. How do you mark it? Ruler. Now, if you're doing running, ruler is probably not the best technology to use there. What's that? Light gauge. Oh, well, if you're really fancy, you can use light gates. GPS. That's one of the things I've actually got. Done my classes, my physics classes in the past to do, is you get on your phone, you can get, there's one called Sports Tracker, which I've used in the past, which basically uses GPS to map what you're going on there. So the thing is though, you can assess it there. So if we do the old school one that you do in year 9, 10, where you use a trundle wheel to mark out 100 metres at 10 metre spots, and you then use a stopwatch to mark that there. That is basically old school technology. You could actually even go back to Galilean times and say, well, I can't afford a stopwatch. What did Galileo use? He used, I think, a water timer or something. Or you think, oh, I'm going to measure time using a sand timer. Probably not that accurate. If you thought, well, no, it's going to measure every 5 seconds. So I'm going to go 5. Okay, that's 5. Now we go back to 10. That there. That's still technology. You've got to remember there, technology doesn't mean high-end computer stuff. It can mean a ruler. A ruler is a piece of technology. You're probably counting 1 Mississippi, 2 Mississippi, 3 Mississippi. That's a bit of a technology. Yes, Sheree?
There's still some coming, but if they wanted a break soon.
Okay.
Yeah.
Okay, well, how about we'll do one more point and then we'll have a break for about 15 minutes. And of course, one of the things there, one of the dot points in there, I talked there about digital technologies. Now, doing an experiment like that, speed one old school, if you're using a trundle wheel, if you never use it, it's a big thing you roll along and every metre it clicks. And so you've got to have someone there going 1, 2, 3. Then you've got to use, if you're really old school, have one of those handheld analog things there. So one of the big things here, most of the instruments you use in science now, particularly if you use your smartphone or a digital device, is basically doing this thing with digital. Okay, now I'll just go across here for a second, back. The one on the right, so that there is an analog instrument. It's not the best photo. As you can see, it's basically got a little lever that moves up and down. When you're doing electricity in junior school, you're probably using these, most schools still have these little ammeters there. This here is a digital device. Now what we have here with our analog and digital, and you do have to understand this a little bit, analog gives a continuous output. So you have to make a judgment on what the level is, whether it's a 1, 5, whatever. Digital gives you a definitive output. Analog is a little bit less accurate because you've got to make a guess. Digital is more accurate. Analog sometimes requires more power. Analog's more sensitive, blah, blah, blah. Basically, when you look at this here, digital gives you a definitive reading. Another advantage of digital is it's very easy to collect the data. You don't need someone there with a pen writing it down. Most digital instruments will actually collect it yourself. Okay, we'll leave it there for the moment. So time's 10:35. Give yourself 15 minutes to go to the toilet and we'll come back at about 10:50. So we just finished the analog digital. Come on. Okay, there we go. Now, what happens here? This is another case here where what we talked about in Module 5 is also in Module 6. And I think to some extent it's also in Module 7 and that there as well. So you're going to talk about random errors. So if we go back to my running physics example there, if we're using stopwatches and that there, what are some random errors in timing? Yeah? Stopwatch working, but it can also be as simple as if you have 10 people on 10 stopwatches measuring the same time, they will all have 10 different variations of the time because they won't start at the exact same time, they won't end at the exact same time. Systematic errors. Where would you get systematic errors in an experiment where you're just timing someone running 100 metres? Where might you screw that up? Yeah? You don't start at 0, yeah. Someone might be lazy and they're just using the lap function or something like that. Or they might be talking to their friends. Oh my God, they're running. Okay, I better start now. Well, that's a stupidity error, really. But yeah, you're systematic. So measuring instruments. The one thing you might have there, yeah, if they don't start, if they use the lap function instead and try and guess half of it there, there's something wrong with the instrument. As I said before, maybe you've got an analog stopwatch, just an old style one, or maybe you've just got a dodgy one that was made in some Chinese prison farm that allegedly don't exist. But just things like that there might be errors with it. And might be wrongly used, which is sort of that one we're saying there, someone doesn't start at the same time. If you ask a monkey to do your stopwatching, then you're probably not going to get accurate results. You need 1 million monkeys at 1 million typewriters. No English people here? Okay. Also one of the things there, you've got to think about work health and safety, chemical data. So some of you in your school probably using this thing here, which comes a thing called Risk Assess. And risk assessment is a huge thing. Previous syllabuses really didn't worry too much about it. They'd say, oh, what's a risk? Here you've really got to think about it here. So if we're doing a chemistry experiment, which some of you have probably done a few of, it's like, what is the risk of something going wrong? Going back to my running experiment, that's not a chemical risk, but what's a risk of doing a running experiment? What was that? Tripping over, falling over. What was that? Surface, yeah, someone tripped, the surface might be slippery. You might just also have people that are incredibly unfit and running 100 metres isn't the best thing to do. You might be like my school, which has a defibrillator in the front office, just in case. And you laugh, we actually had to use it 2 years ago on a visitor. You've got there as well, one of the things here, I've had conversations with a lot of people, risk assessment. One of the things there, be careful with risk assessments and things like this as well. This here, oh my God, there's red things there. It must be really, really dangerous. It's only really dangerous if you swallow it. Now, when it says skin irritation, means if you don't wash it after 5 hours, it might irritate your skin. There's many reagents we use in school actually will cause you this risk. You're stupid, which goes back to our systematic thing there of people not doing the right thing. Respiratory irritation, yeah, don't breathe any chemicals in. Okay, pretty straightforward. And toxic to aquatic life. although toxic to long-lasting effects, yeah, not good if you're a fish. So if you're not a fish, it's not a bad chemical to use. In terms of that there, if it says 7 to 12, it usually means it's pretty easy to use. So this one here is an interesting little one here. Yes, I did like that. I did see one which I couldn't put on here, which had a very interesting word as their password. Technology helps in developing things. So we got 4 examples. Now you don't, when it gives you like 4 or 5 examples, you don't need to memorize them in great depth. You just have to know about them essentially and how they kind of work. So computerized simulations and models of the Earth's geological history. X-ray diffraction, DNA. Technology to detect radioactivity, atomic theory, and the Hadron Collider and the discovery of the Higgs boson. Okay, I don't need to know a physics background of the Higgs boson. I have trouble understanding it myself, and I don't really understand it. I just know the basics of it. But let's have a look. First one there. New computer modeling, blah, 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 blah. That's a lot of stuff there. How old's the theory of plate tectonics? No, it's not. Any geologist will help me here, but the guy who supposedly did it, Alfred Wegener, I think it was the late 1800s, he proposed it. It only got accepted in the 1960s. So the theory of continental drift and plate tectonics is, compared to what else we do, is actually quite new science there. But I throw this in here because one of the things there, computer modelling has allowed scientists to actually make really good predictions. What's another area of science that's used computer modelling a lot? Climate change, things like that. Tectonic activity below the Earth's surface is very complex. It's one of those things, one of the reasons that it's hard science is it's very hard to drill down and actually observe the mantle in action. You've got to rely on a lot of secondary evidence. Earthquakes have provided a lot of that there. But computer modelling it's kind of a bit, when I was doing my uni degree a very long time ago, geologists were short people with beards. The men had moustaches as well. But most geological stuff now, I actually do have geology in my degree. But a lot of it now, there's field work, but there's a lot of computer modelling. Hell of a lot of computer modelling to try and predict. And so one of the biggest things they're trying to do with this is if you can understand the models behind tectonic plates, what might you be able to predict with accuracy? Earthquakes. Okay, awesome. That's one of the things there. There was a very weird thing. It was about 5 or 6 years ago. In Italy, 7 geologists were arrested for manslaughter because they failed to predict an earthquake. Now, I could be wrong on the manslaughter charge, but they were definitely charged with crimes. It was eventually thrown out, and if you know anything about particularly Italian and Greek legal systems, they're a bit nuts. But what we've got there is that if you can predict it, you can actually potentially save a lot of lives. Now, of course, in Australia, we're pretty lucky. I think the last earthquake, or the only earthquake to really kill people, was the Newcastle one in 1991. And that wasn't the earthquake that killed them, it was the collapse of stuff because Newcastle is a mining town. And of course, Australia is pretty tectonically safe. I was trying to think of a fancy word. Of course, we all know the story of Rosalind Franklin, X-ray diffraction. She was the woman that pretty much did the work that led to the structure of DNA and the double helix. And of course, it is promoted in a lot of ways there. You know, she was screwed up by one of her work. I can't remember. It wasn't Watson or Crick. It was another. Does anyone know that? Who was that? Yeah. It was her PhD supervisor or something like that. He basically, because one of the things there, she was doing this in the late 1940s, early 1950s, and being a woman and doing science then, it was kind of a little misogynistic. You know, she's just a little girl. She's fine. I'll take her pretty pictures and show it to the real men who can do this. And of course, is it James Watson who's just got stripped of a whole heap of things? Because apparently one of the discoverers of DNA is a completely racist, bigoted, or old, elderly white man who said, you know, black people aren't that smart. I'm sure DNA proves that. So of course, she didn't get the Nobel Prize, and a lot of people say, oh, she didn't get it because she was a woman. She was actually dead by the time they got the Nobel Prize, and the Nobel Committee does not give someone a prize if they're dead. So you would hope that she would have got it if she was alive, but there's nothing to do with that there. Of course, that there is a little bit of an X-ray picture, and it shows you a bit of the structure. DNA is a double helix. It goes in on itself. Now, what that was able to do, and the reason this is an important thing here, is that the X-ray crystallography, an experimental method in physics, helped discover an important structure in biology. That important structure in biology has led to basically the modern world being dependent on biotechnology. And so that technology led to a discovery which has led to more technology. So all this stuff, and we talk about it a little bit later, you know, biotechnology, genetic engineering and that, are technologies that came about because of a discovery made by a completely different technology. A little bit like Doppler before. He was studying stars, discovered a shift in the stars, which led to other discoveries in sound and waves and things like that. Radioactivity. Atomic theory. Any physicists here will recognise, do I zoom in there? Yes. What is that? Cathode ray tube. Okay, so the cathode ray tube, now was it Crook that eventually did it originally? Basically that is a glass tube where most of the air has been sucked out. So it's pretty much a vacuum, or as much of a vacuum as you can get on Earth. At this end here is the cathode, and that's firing out a whole heap of electrons. When this was invented, they didn't know that. And so all they knew was that there was this magical green glow coming out. They called it cathode rays because it came from the cathode. What that led to was the discovery of the electron. And that led to help me here. Thomson was the plum pudding model. So Dalton came up with the idea of the atom, and then Thomson used this sort of thing here, saying that atoms were made of this big blobby positive stuff that had little electrons in it. This also led to other discoveries. So essentially what you can also do is think about this technology led to discoveries about the atom, which led to discoveries about electricity, which led to discoveries that pretty much the entire modern world with chips and things like that is based on. So technology has come, so you could say technology in physics has been influenced by chemistry. You can say chemistry is pretty much the physics of the electron for those chemistry teachers here who are going to yell at me. Now, of course, again, you also had there as well, this is Rutherford's famous gold foil experiment. So what he did here, he's got an alpha source there, fires it out, fires this thin gold film, which is, I think was less than 10 atoms thick. It was essentially a see-through gold sheet. One of his research assistants must have been there for days just hammering. Oh my God, I've broken it, I've got to do it again. And so what they did there, goes through there, and most of it goes through. What does that tell you about atoms? Come on, anyone? They are very small, but what are they mostly made of? They are, but 99% of the atom is empty. Okay. And so what we got here, was something stupid like 99.9% go through, 0.1 or something get deflected, and an infant 1 in 10,000 get bounced back. So what we've got there is the Crookes tube led to this experiment, which led to a better understanding of the atom, which eventually so this was, I think, 1911, early, about the same time the Titanic was being sunk. And 30 years later, what did the discovery of the atom lead to? Or discovery of the parts of the atom lead to? Around 1945. Atomic bombs. Okay. So one technology, so a discovery in one area leads to this here. And I think that's the intention of this outcome, is that, it's not just one thing happens and then that's the end. It's this thing leads to this thing, to this thing, to this thing. And of course there, if we had days to do this, I'd be showing you some of the old 1960s atomic things there. If you look up on the internet, it's a thing called, I think it's called A is for Atom. It's an old 1960s educational film saying atoms are awesome. You're going to have a nuclear reactor in your backyard. And of course, this one here, the Large Hadron Collider and discovery of the Higgs boson. Now this is a little bit different to the other ones here because this is a very open-ended one here. The CERN is it's in French. Is it something European research? Yeah, but it's in French, so they're all round the wrong way and everything. But it's basically CERN is the world's, I suppose you'd say it's the world's biggest lab. Now I think here, what do we got here? 1 mile is 2.4 kilometres? 1.6? There's 3 countries in the world that still use imperial. US, some dodgy European country and some dodgy South American country. So this is, I think if you do it, it's about, I think it's nearly 30 kilometres across. It's either 30 kilometres across or 30 kilometres in circumference. It is the world's biggest, it is the world's most expensive experiment ever. And you can see there, you got a little thing here, it's all underground. Okay, it goes between, is it Austria and France or France and Germany, or it goes across 2 or 3 countries. A little bit like the Tour de France. They go up one mountain and down the other one there. But it was set up basically to try and get closer to understanding the nature of the atom. And I think that's called the Atlas device. That's one of their measuring machines. And I think you can see there, that's one of the platforms there. So that's probably a guy, if you had a guy there, it'd probably be about yay big. It's a pretty big instrument. It's expensive. It costs $1 to 2 billion years to run, $1 or $2 billion a year to run. I think it costs about $20 to $30 billion to produce. And we talk about it in the last module as well because it's a good example of cooperation. Now, the reason this is a bit different to the other examples is that the benefits of this research aren't really known yet. We discovered this thing called the Higgs field. So if those of you doing physics, when you get to the last bit there, you talk about the standard model of matter. It's saying that we don't have protons, neutrons, electrons, we have quarks, bosons, leptons, things like that. In this case here, this may lead to technology in the future. And so this is an example which can evolve because unlike, say, the one there just about the DNA discovery in physics led to the discovery of the structured DNA, which led to a whole range of biotechnologies. We don't yet know where this is going to lead. I think part of the hope is that this will lead to some really fast computer applications, technological applications in the future. 40 years ago, the head of IBM, I think it was, said, there'll probably be a need for 6 computers in the world. And now most of you, I think I own at least 6 computers myself personally. Okay? This will lead to stuff that we don't know what we're going to do there. Now, this is another one. How has helped in the following? We quickly talked about this one, the laws of reflection and refraction. Reflection, light bounces off a surface. Refraction is that it bends through a thing there. Now, you don't really need to know the physics behind this because it's not really important. You just need to know that this is used in telescopes and microscopes. Okay? For the most part, it's usually the refraction is the biggest one there. Even though I am a physics background, I've not really done a lot on astronomy, and someone can help me here. I think refracting telescopes are more accurate than reflecting telescopes. Or is it the other way around? Either way, refraction is a really important thing in terms of being able to observe things outside our normal observable range. Okay? And you probably did this in year 9. You did a bit of Snell's law stuff. Angle of reflection is equal to angle of incidence and that there. Look, I don't think you're going to be asked to go into too much detail about that, other than to pretty much say that how did an understanding of refraction and reflection help the development of the telescope? How did it do that? What did an understanding of those two concepts mean for telescopes and microscopes? What did it do to them? What do you always try and do in any scientific instrument? Someone said improve. Yeah, improvement. So a conventional light microscope can magnify things up to about 1,000 times. Anton von Leeuwenhoek, who is the guy who is credited, Dutch guy credited with doing the first microscope, I think that increased things maybe up to about 5 or 6 times. But better understanding of this. Galileo, who's the first person to use a telescope for scientific purposes, prior to the telescope, or whatever other Italian gentlemen were doing outside their windows. You can look at that closely, but Galileo was the first one to look up at the night sky and say, wow, Jupiter has moons around it. He got sentenced to death for doing that, but he advanced science. He basically made them stronger. Now, this one here, radioactive decay and the development of nuclear bombs. So those of you who've done a little bit of chemistry, maybe up to year 11, or a bit of physics as well, because this is a big thing in the year 12 physics course now, we have 3 types of we have 3 types of nuclear radiation: alpha, beta, and gamma. And they all involve this same process. They all involve an atom or a nucleus here getting really excited and then breaking apart. Okay? And that understanding, from what we said before, the Crookes tube to its gold foil experiment to, Geiger and Mars, and there's a whole heap of range here. Within the space of 40 years, you went from understanding a bit of the structure of the atom to being able to build bombs from it. Okay? And so you can argue both ways. In the age of climate change debate, nuclear power is being touted as a possible thing. I personally don't think it's the answer, but it doesn't have gases. It just has pollution that lasts for millions, if not billions of years. Don't know which one's worse. But you also have here that even though it's very hard to argue that a nuclear bomb is a good thing, nuclear technology has actually led to some pretty good technologies. So here you've got basically nuclear medicine. I took a whole heap of my students a couple of weeks ago to ANSTO, Lucas Heights, which is Australia's only working nuclear reactor. And we had a look there. That its sole job, or it's got 2 main jobs. One is to produce nuclear medicines. The other one is fundamental research. And so from that there, you've got here oncology, which is just the doctoring of cancer. Get radiotherapy. Now, one little distinction there, radiotherapy and chemotherapy are 2 different things. Radiotherapy is radiation, chemo is chemicals. Okay, so you got here, what do we got here? Tumours with difficult delivery. You might have a tumour, particularly brain tumours are probably the hardest one there. They can actually use a focused X-ray or a radiation gamma beam to actually target a tumour. It's a non-invasive technique. Now, of course, in any of these therapies, it will kill other healthy cells, but it's a balance. Medicine's a balance between causing a little bit of harm for greater good or someone dying. And then that's probably a hard thing there. So, of course, here, in this case here, it's nuclear technology is a positive thing. Of course, we do know the bad thing there, and it's been a while since we've had nuclear bombs go off. I think the last one was North Korea, and it was very interesting that North Korea said, yeah, we'll talk to you after their nuclear facility had actually collapsed because they blew up too many bombs. DNA. We hinted to this before, and we'll talk about this a little bit later as well, this idea of GMOs, genetically modified organisms. Now, a lot of people, I think, do I zoom in here? Yep. GMO, human manipulation of DNA. Now, a lot of people say, oh my God, GMOs are so bad. They're the worst thing ever. Humans have been genetically modifying food for thousands upon thousands of years. Do you think a carrot looks like that? Carrots only are orange because a Dutch king 200 years ago actually liked orange, and the majority of European carrots were done in the Netherlands. And so all the farmers crossbred everything so all the carrots were orange. If you want to be like a complete hipster, you go to some organic market and you get purple, orange, white, black, whole heap of different carrots. The banana looks like that. Banana is, and a biologist can help me here, banana is essentially just a bit of leaf that's gone that way. Tomatoes, 500 years ago, were actually poisonous. They were genetically modified. I think it was the seeds contain arsenic or something, or is that apples? Come on, biologists, help me here. Basically, my point is, okay, what's the most common plant food source in the world? Not what? Grain. Rice, it's probably wheat is probably the biggest one, but wheat and rice come from the same thing. They come from grass. They are modified grasses which have been changed over time so that the seeds have been crossbred to become bigger. Dogs are an example of genetic engineering that's occurred over 10, 15,000 years. Dogs are essentially domesticated wolves. Okay? A pug does not look like a pug. A pug looks like a pug because some Chinese emperor 1,000 years ago thought that dogs that had short noses were more regal than long dogs. And so all these courtesans and all that basically bred all the short-nosed dogs together. So unfortunately, pugs are really cute, but they're also inbred because that was the easiest and quickest way to do that. Studies in GMOs. Now, again, I've taken this infographic from probably a pro-GMO thing. You can probably find ones that are against it. There really isn't much research that shows GMOs have caused any long-term damage. Of course, we can say that as well. The cigarette companies for a long time said smoking was healthy. But, you know, and the thing is probably, as I said before, every food you eat is a GMO in some way, shape or form. Now this one here, this is an interesting one. When I did it with my class the first time, it was a bit of a weird one. I couldn't actually find any real big information on this. But Newton's laws and technology for earthquakes. Basically, you have to look at Japan. And the way you think about that there is that Newton's laws, for those who've done physics, you got first law is inertia, second law is F is equal to ma, so the amount of acceleration from a force is related to mass. And the last one is, third one is for every action is equal opposite reaction. So what we've got in this case here, that when an earthquake occurs, there's forces involved. And do I zoom in? Yep, so we've got here, this is from an article which says basically you can use different materials. There's a lot of materials that are used here. Probably the most common way of using knowledge of forces to stop earthquakes causing damage is this here. And this is the way I think most Japanese skyscrapers are built. Japan is one of the most densely populated countries in the major cities. You know, I've never been to Tokyo. Yeah, Tokyo is the capital of Japan, isn't it? Yeah, thanks geographers. Has anyone here been to Tokyo? Yep. What's the city like? Very big, and it's a ton of skyscrapers. Japan also is probably the biggest westernized city. It gets a hell of a lot of earthquakes, but you never ever hear about a Japan skyscraper falling down. And that's because when they started building these tall buildings, they had to think of ways of stopping them from collapsing. Okay, and as you know from the news in the last couple of months, if anyone, if there was an earthquake under Mascot, all those high-rise towers would probably all collapse because we're not an earthquake-prone country, and unfortunately half of our developers are pretty dodgy by the look of it. Oh, what you got here? Most of these buildings have these little things under here, and so when an earthquake occurs, these things, these little pillars here, and they're made with this thing, in this case here, it's an example of a material called biotextile. But a lot of them actually have springs under them. Japanese high-rises are often designed so that if an earthquake hits, the building actually sways. Now, I think if you've got a penthouse apartment in a building that's swaying by about 10 metres, I'm not sure I want to be in that building, but it obviously works because, you know, you don't have collapses there. Okay, now here is last little one here. I'm only going to cover this briefly because it actually comes up a little bit later. And this is about this idea of Indigenous cultures and this idea of ethically working with them, particularly with this thing called bioharvesting. Bioharvesting it can also be used with a term called biopirating. And essentially what you're doing is you go out and you try and find useful chemicals in Indigenous areas or in areas with there. So one of the things there, aspirin. Aspirin is one of the first commercially made painkillers. Does anyone know where aspirin was originally found? I think I heard it over here. Yeah? No, you're just playing with the stress ball. Aspirin came from the bark of a certain tree. And they've noticed that certain people, certain countries, certain ethnic groups, if they had a headache, toothache or something, they'd actually chew this bark. They found there was an active ingredient. And so what we've got here is that we'll go into a lot of detail a little bit later. Okay, let's quickly do another quiz. Okay, good. Most of you remember that graph. Come on, you should get this one. It'd be very accurate, it'd be a pain to use though. Now the reason it's not the atomic clock, it's not the most appropriate, it's a pain in the butt to use in that situation. Some of you are doing it too fast and getting the wrong answer. 2024, where are you? Okay. You're only halfway there. I can understand why people did put exploitation. Okay, it's getting close to the top there. Who's 1920? It's you idiots again, isn't it? Yeah. Remember, the term scientific theory is very different to the common use. Okay, is this the last one? I think this is the last one. Very tight. Okay, when I hit the next button, 1384. All right, well done. Okay, so look, I think you guys are actually doing pretty well with those now. There we go. 1384, 2009. So what do we got? That's only a few hundredths of a second between you guys there, so that's actually really good. So what we're going to very, very quickly do though is go into the 9-question one, which is for the next module. Okay, so we're hosting it live. There we go. That's all right, some of these nested questions are a bit tricky. Okay, this is 1912 and 1926. Okay, this is between you two really here at the end. Okay, there we go. 1926 in the middle there. Okay, guys.